Hi, in this video, I'm going to solve this very interesting math question that came up on a Greek math Olympiad. Here's what it says. If this equation, quadratic equation ax square plus c minus bx plus e minus d equal to 0 has real roots greater than 1, prove that this fourth degree equation ax to the 4 plus bx cube plus cx square plus dx plus e equal to 0 has at least one real root. So, given that the first equation, a quadratic, has real roots greater than 1, we have to prove that the second equation, which is a fourth degree equation, has at least one real root. So, if I just reframe this a little bit and take this quadratic expression to be the polynomial p of x, then we are told that p of x equal to 0, this equation, has real roots greater than 1, or p of x has real zeros greater than 1. Then if I take this polynomial to be q of x, then I have to prove that the equation q of x equal to 0 has at least one real root, or in other words, the polynomial q of x has at least one real 0. What does that mean really? What does that mean in terms of the behavior of q of x? What are we trying to prove? So, if we have to prove that q of x has at least one real 0, uh, if we are able to prove that the graph of q of x cuts the x-axis at least once, that is what I am going to try and prove here. If the graph of the polynomial q of x cuts the x-axis at least once, then we will be done, because that will mean that q of x is 0 for at least one value of x. So, q of x has at least one real 0, or this equation has at least one real root. Alright. So, how do we go about this? Well, if I take the polynomial q of x, which is ax to the 4 plus bx cube plus cx square plus dx plus e. What I am going to try and do here is somehow express this expression in terms of p of x, because I know something about p of x. I know that p of x has real zeros greater than 1. So, somehow I am going to express q of x in terms of p of x and see where that gets me. So, how do I do that? I have this first term ax to the 4, which I can write as ax square squared, and this now resembles this term ax square of p of x, but the variable here is x squared and not x. And then the second term here, the linear term, is c minus bx. I already have a cx square here, which I write like this, but then I need a minus b. So, what I will do is I will introduce a new term minus bx squared here, because remember the variable here is x square. So, I introduce this term minus bx square, but this term does not exist in the original expression of q of x. So, I also add this term back so that my expression does not change like this. And then I have e minus d here, I have an e here, so I copy this e down, but then I also need a minus d. So, I will write a minus d like this, but I will also add it back so that my expression does not change. And what am I left with now? I have these terms bx cube and dx. So, let me write these two terms bx cube plus dx, and here we are. So, what I have done here is just rearranged the expression of q of x to get these terms. And if I rewrite this, what do I get? A x square squared plus c minus b times x square plus e minus d. And I'll just copy these. I can factorize this, take out an x common. So, x times bx square plus d plus I copy this bx square plus d, and this is where we are. And now what I want you to observe is that this expression, what is this really? If you compare it with the structure of p of x, this is actually the polynomial p, but with the variable x square. So, that is what I was trying to get to. So, this is p of x square. You just substitute, instead of x you substitute x square, you get this expression here, and then you have this term plus this term. So, you take out the bx square plus d common. So, you get 1 plus x, because this is bx square plus d times 1, this is bx square plus d times x. So what you'll get here is 1 plus x times bx square plus d, and this is how we have managed to write the polynomial q of x. So that's amazing, because what we have done is we have written q of x in terms of the polynomial p, and we know something about p. What do we know about p? We are told that p of x has real zeros greater than 1. So let's make use of this fact. So let's say that one of the 0 of p of x is k, and we know that k is greater than 1, which means that p of k should be equal to 0. Now, can I somehow use this constant k in this expression? If I substitute x equal to k into this expression, I get q of k equal to p of k squared plus something here, but that doesn't really help me because I get p of k squared. But what I know is that p of k is 0, and this is what I want to try and use. So what should I substitute here so I get p of k in this expression? It's obvious that we should substitute x equal to root k into this expression, into this equation. So we will get q of root k is equal to p of k, because it's x squared, plus 1 plus root k times bx square, which is bk, plus d. Amazing. Now remember that I am trying to prove that the polynomial qx cuts the x-axis at least once, it changes sign. So what else could I substitute into this equation here, so I get another value of q at some point that could be the negative of this? If you think about it a little bit, the answer could strike you quite quickly, because we have an x squared here, and therefore if I substitute x equal to minus root k in this equation that I've written between q of x and p of x, this also tells me something very interesting. So I have q of minus root k is equal to p of k, p of k again, because x square and x is minus root k, so the square is k, plus 1 minus root k times bx square plus d, which is bk plus d. All right, and now we arrive at a very interesting conclusion. Q of root k is this expression in which p of k is 0. So q of root k is this term here, this product here, and q of minus root k, this term is again 0. So q of minus root k is this product here. Now I want you to observe these two products carefully. This part is common, bk plus d, and this multiplier here is 1 plus root k here and 1 minus root k here. Now we know that k is greater than 1, which means that root of k will also be greater than 1. So root of k must also be greater than 1, which means that 1 plus root k will be greater than 0, but 1 minus root k, this will be less than 0, because root k is greater than 1. And this means that this first product here and the second product here, these two products will be of opposite signs, and that is what I was really trying to prove. So these two are of opposite signs, which means that q of root k and q of minus root k are of opposite signs. So what does that mean? Well, it means that if I were to draw the graph of q of x, let's say this is x equal to root k and this is x equal to minus root k, and what this means is that q of root k is of one sign. Let's say q of root k is positive somewhere here, and so this is, I'm plotting q of x against x. So q of root k is positive, but q of minus root k will then be negative, it will be of the opposite sign. And by the intermediate value theorem, because q of x is a continuous function, it's a polynomial, the graph of q of x must cross the x-axis at least once. It could cross it more than once, but it must cross it at least once, which means that we will get at least one real 0 of q of x, and that proves what we set out to prove. So let me just recap what we did. So essentially we took the polynomial q of x, we rewrote and rearranged its expression so that we could express it in the form of the polynomial p, but the variable here was p of x squared, plus we got this expression. And then we knew that there is the zeros of p of x are greater than 1. So, we took one of those zeros and we substituted the root of that 0, which is root k, into this equation that we got, and we also substituted the negative of that root. So, negative of root of k, and we got some other expression, and we were able to show that these two are of opposite signs. So, q of x changes sign, which means it has at least one real 0, or the equation q of x equal to 0 has at least one real root. So, that completes our proof. I find it very elegant, a very elegant use of the intermediate value theorem. I hope you liked it as well, and if you have any other way of solving this question, do share it with us. I would love to know what any alternative approaches here are. Thank you, and I hope you enjoyed it.